theoretical collaborator is Dr. Bhattacharya. So before getting into microwaves, I would like to discuss briefly what are microwaves. So, and why we use microwave and what are the essential benefits. So if you look at conventional heating, there's a heat source on the surface, and when you put a burn in a material, and with the material the heat is transported by conductive transport mechanism. And of course it radiates from the source to surface, but volumetrically heat transport is basically the conduction transport and essentially surface heating. In contrast, if you go to microwave heating, and in the microwave essentially we talk about dielectrics. And what are dielectrics? Dielectrics are different kind of dipoles such as plus and minus, and generally when there is no microwave, in absence of microwave incidence, what actually happens is dipoles are actually randomly oriented, and essentially plus or minus will actually cancel each other, and we don't have essentially any kind of induced electric field. So when we have uniform electric wave, uniform electromagnetic wave, where electric field and magnetic field are perpendicular to the direction of wave propagation, what actually happens that dipoles try to see the arrow direction, they try to orient along the electric field, and when they orient along the electric field, a resultant field direction actually will develop, and it's called induced electric field. So there's a difference between the incident electric field and the induced electric field. And basically what are the results, what are the response mechanism actually represented by the material properties. This is called dielectric constant and dielectric loss. Dielectric constant is actually ability to store electromagnetic energy. Essentially, if you look at philosophically, what is that? We just actually, the spring, you just stretch it and just remove it, you just see the bump, and that's nothing but dielectric constant, analogs. And dielectric loss is just like, if you rub your hand, just after some time it will get heated. That's dielectric loss, so easy to actually visualize. So ability to convert electromagnetic energy into heat, and that gives the volumetric heating mechanism. Remember, there's a surface heating mechanism, and there's a volumetric heating. So what essentially it does, the volumetric heating mechanism, we have the conductive heat transport. Essentially, every point generates the heat. How it is generating, it is not that trivial, it's complicated, and that's what we'll be going to address in the next couple of slides. So geometric configurations, what we are planning to consider here, we are planning to consider cylindrical geometry, and we have two different kind of square geometry. One is the usual configuration, another is rotated. And why we have considered there is some kind of scattering pattern, electromagnetic scattering pattern based on antenna theory that we are trying to summarize in a couple of slides. And there are two kind of mechanisms. One is called lateral irradiation, and one is called radial irradiation. Lateral irradiation is actually uniform electric field, is propagates from one direction, and radial irradiation is actually when you have the turntable, the plate is moving, and in that case you can actually have analogous static formulation, which is from all the sides. We want to see this is all basically essentially wave propagation. How the waves actually when the wave propagates the material, a lot of interesting thing happens. So actually incident is like a field of electromagnetic wave, and some reflection will occur, and there are some kind of further transmission. And when the reflection occurs and the incident field occurs, and they do have the interference pattern, and that leads to constructive interference and destructive interference. So we'll proceed further, and let's see how they occur. So in a mathematical format, essentially, when electromagnetic wave propagates, we know our Maxwell's equation, Helmholtz field equation, that's grad square E plus k square equal to 0. But this is a different kind of format I'm presenting here. Is a wavelength within the material and the penetration depth within the material. And I is the imaginary quantity. As I mentioned that this actually emanates from a quantity called propagation constant, which is a complex quantity, and has the real part is the dielectric constant, and imaginary part is dielectric loss. I'm not going to much of the mathematical details. I'm just trying to glimpse of mathematical foundations here. So we have the lateral irradiation, where the electromagnetic wave is coming in one direction. Microwave is coming in one direction. Okay, And this is a typical sample. You can see that the sample, the blue color, which is having irregular size, could be circle, could be square, could be an irregular size, shape. And this is the hypothetical circular domain. That is for the implementation of boundary condition. I will come back in a few seconds. And this is a radial irradiation where I mentioned that on all the directions, the field is actually microwave is propagated. So what actually happens when we would like to solve the electromagnetic wave equation, we need to have the boundary condition. The boundary condition is not that straightforward. The boundary condition says that the interface electromagnetic field the material and the free space, they should be continuous. They should be continuous, and the same for the magnetic field or derivative of the electric field. So when we implement that, it actually, the electric field, when you talk in terms of material, it is so complicated. I would like to try my best to make you to understand that it has the interference of the transmission and the reflection. Transmitted electric field for this kind of circular domain could be represented by Bessel function, and the reflection by the Hankel function. So, and when you implement the boundary condition, there are the orthogonality criteria. And orthogonality criteria can be best implemented in the circular domain, and that's what we decided to construct the circular domain, which is having the medium air. So, what is actually happening is that EM is the material electric field, is the free space, and we will implement the boundary condition here. So, our computational domain is here, boundary condition is implemented here, by the solution will propagate, and essentially we get the solution. It's a bit challenging, and this kind of things have been benchmarked with the analytical solution, but when you couple with the energy balance equation, you need to solve numerical. So, if you look at this is the equation for the within the material, which is by the blue shaded domain, and these are light shaded domain with the Helmholtz wave equation for the free space. And if you look at the two length scale, which is the wavelength and penetration depth for the material, and we need to have only the wavelength in the free space, because penetration depth is leading to 0 for the free space. So we implement the boundary condition along the surface, and what we get something called radiation boundary condition. It's not a radiation boundary condition where you talk in radiation heat transfer. It is called RBCE in microwave heating. So what we get a complicated, it is called Robin's mixed boundary condition in mathematical term, and which has the which is having integral differential format in nature. And this kind of stuff which cannot be solved easily in the finite difference and the finite volume method, and we'll be discussing that how it can be automatically implemented using finite element method with the automatically boundary condition built in format. So similarly, one can actually see the more Robin's mixed boundary condition for the radial irradiation. If you look at the length scale here, lambda m and dp and lambda 0, these are the wavelength and the penetration depth, but in the radiation boundary condition, you can see we have only free space length scale. So after that, we'll see that how can we have any kind of material invariant characteristics within the microwave domain. So what I'm trying to say that let me talk about a bit on the convection heat transfer. We have Rayleigh number, Grashof number, Reynolds number. Can we have these kind of numbers in microwave? Of course, the answer is yes. And when we have now we can see that entire microwave propagation has seen the function of wavelength of microwave within the sample, penetration depth of the microwave within the sample, and wavelength of the microwave within the free space. That's lambda m dp and lambda 0 respectively. So with that, it is possible to have the two-dimensionless numbers, Fp and Fw. And with this Fp and Fw, we can actually have material invariant characteristics. That means that if we have material invariant characteristics with the material invariant format, we can have a whole lot of materials. And if you have the map with you, we can actually predict, or you can forecast the heating pattern within the microwave, which is practically very much non-trivial. And there are a lot of counterintuitive issues which will be addressed in a couple of slides. So what we have done, we have categorized in group 1, group 2,